All right, today we're going to dive into a really fascinating new way of thinking about robot intelligence. It's called LOHO Manip. And look, this isn't about just making a robot a tiny bit better at some simple task. No, this is about teaching it how to run a marathon, to handle those long, complicated jobs with a ton of steps, the kind of stuff we do all day without even thinking about it. So let's see how they're teaching these machines to finally go the distance.
So, take a look at this. You've got a can of veggies, a couple of toy foods, some stuffed animals. And the instruction is simple. Organize this table. Put all the food on the red plate and the rest in the black box. Easy, right? For a person, this is nothing. You'd probably have it done in, 10, 15 seconds? But for a robot, this simple command is actually a massive, massive challenge.
So why is this so ridiculously hard for a robot? Well, it's because that one little sentence isn't one action. It's a whole cascade of them. The robot has to see everything, figure out what's food and what's not, and then plan out this whole sequence of picking things up and putting them down one by one. And if it makes one tiny mistake, just one little slip up, like bumping into something or misidentifying an object, the whole plan can just completely fall apart. This is exactly where most modern robots get stuck. And that brings us right to the heart of this research, something called the long horizon problem. It's this fundamental roadblock in robotics, and it's all about how these tiny little errors can snowball over time and just cause the whole mission to fail. Let's put a pin in that definition. Long horizon manipulation. We're talking about any task that has a whole bunch of steps that all depend on each other. Think about making a cup of coffee. You have to get the mug, then get the coffee, then fill the machine. Each step has to happen in order. If you drop the mug right at the beginning, well, the whole process is over. The longer that chain of actions is, the more chances there are for one little thing to go wrong and just derail the entire operation. And this is where current AI models really struggle. These vision language action models, the VLAs that power a lot of today's best robots, they're sprinters. They are amazing at short one-off commands like, hey, pick up that red block. But you ask them to run a marathon, to do a long, complex sequence, and they just fall flat. They don't have that ability to plan ahead, to keep track of their progress, and most importantly, to recover when they inevitably make a mistake. So, how do we fix this? The researchers behind LOHO Manip came up with a pretty brilliant solution, and it's actually inspired by how we humans get things done. Instead of having one giant AI brain trying to do everything, they split the job in two. You've got a high-level manager that does the thinking and a low-level worker that just does the work.
And this slide really shows you the difference. The old way, that's the monolithic approach on the left, is to have one giant AI that has to do it all. It has to understand the goal, create this perfect multi-step plan from beginning to end, and then execute every little movement flawlessly. It's incredibly fragile. The slightest change in the real world, and the whole plan is toast. But LOHO Manip's approach on the right is so much smarter. You have a task manager, a smart language model, whose only job is to look at the big picture and decide, okay, what's the very next thing we need to do? Then you have the executor, which is a standard robot controller, and its job is way simpler. Just do that one next thing. This makes the whole system so much more flexible and tough.
So what does that manager actually give the worker? It doesn't just yell out an order. It provides a really specific, really helpful set of instructions. Think of it like a little digital roadmap for just the next action. Okay, here's how it plays out moment to moment. First, the manager takes a look at the table, just as it is right now. Second, it makes a little text-based to-do list of everything that still needs to get done. It's not planning the whole thing out again, it's just updating its list. And third, and this is the really genius part, it creates something they call a visual trace. It literally draws a path right on the video feed for the robot arm to follow. And here you can see exactly what that looks like. See that yellow dotted line? That's the trace. The manager is essentially telling the executor, hey, forget about the whole organize the table thing for a second. Your only job right now is to move your hand along this yellow path and grab this one object. This is brilliant because it takes this big, abstract, long-term goal and turns it into a super simple, concrete, short-term problem that these robot controllers are already fantastic at solving. Now, the real secret sauce here is a concept called receding horizon planning. Okay, so a normal robot might make a full 10-step plan at the very beginning and then just try to follow it blindly. LOHO Manipulate is totally different. The manager doesn't just plan once. It looks at the world, it makes a plan for the very next step, it waits for the robot to do it, and then it looks again and makes a brand new plan based on what the world looks like now. It's constantly reassessing. And this is why that constant replanning is such a game changer. Just look at this example. The robot was supposed to grab the corn and put it on the plate. But on the right, you can see it messed up. It grabbed the sushi by mistake. Now, in an old system, that would be it. Game over, failure. But with LOHO Manip, the manager just looks at the scene again. It sees the corn is still sitting there, so it just updates its to-do list, basically thinks, whoops, that's not corn, let's drop this first, and it draws a brand new trace to fix the mistake. This is automatic error recovery, just built right into the system's core loop. It's amazing. Okay, so the theory is beautiful, it's elegant, but does it actually hold up in the real world? Let's check out the results and see how this thing really performs. Let's circle back to that original task. Organize the table, food on the plate, toys in the box. This slide shows you the whole thing, all 10 steps, playing out perfectly. The manager first spots the brown toy, draws a trace to pick it up, that's step 1, then draws another trace to drop it in the box, step 2. Then it moves on to the can of peas, picking it up in step 3, placing it on the plate in step 4. And it just keeps going, step by methodical step, for every single item until the job is done. A perfect, clean execution of a really complex task. And the numbers really tell the story. This chart shows you the performance on a standard test for these long horizon tasks. It's called the Libre benchmark. Other top-of-the-line models, they average about an 86.6% success rate, which is pretty good. But LOHO Manip hits 97.5%. Now that jump of over 10 percentage points, that is massive in the world of robotics. That's the difference between a robot that kind of works most of the time and a robot you can actually rely on. But this might be the most important result of all. The system isn't just memorizing how to do things, it can actually generalize. Here, it gets a way more abstract command. As you prepare the vegetable skewers, think about incorporating a sweet and smoky element. And from just that, the manager correctly figures out it should grab the BBQ sauce, an object it might not have seen before, and move it over. This works because that high-level manager is great at understanding language, and the visual trace lets it guide the worker to interact with things it's never been trained on. So let's zoom out. What does all this mean for the future of robots? I mean, this is about way more than just cleaning up a table. This feels like a fundamental shift in how we design intelligent machines. Let's just quickly recap the big ones here. First, modularity. Since the manager and the worker are separate, you can upgrade them on their own. You could drop in a smarter language model as your manager or a faster robot arm as your worker, and you don't have to rebuild the entire system. Second, that automatic recovery. This is just huge. The constant replanning means the robot can just naturally recover from its own slip-ups. And third, better generalization. That visual trace acts like a bridge, letting a smart brain guide a simple body to do new things in new situations. So the main thing to take away from all this is that LOHO Manip isn't just a cool one-off demo. It's a powerful and scalable blueprint. It's an architecture for building robots that can finally start to handle the messy, unpredictable nature of the real world and move beyond the sterile, perfect environment of the research lab. And that leaves us with one last, pretty exciting question. For decades, we've all been hearing about the promise of helper robots in our homes, and this ability to understand complex goals and to gracefully recover from errors has always been the missing piece of the puzzle. So, is this kind of decoupled, constantly replanning system the breakthrough that will finally make that promise a reality?